Okay, good morning, everyone. I'm Yi, a graduate student here at UCSB working with Joe, and I'm very grateful for this great opportunity to present my current work on inferring the high-Z Quasar properties with the light echo method Christina has just talked about.
I don't know this.
Sorry. Okay. Okay, the background of this work is that, well, the observed high-Z quasars, namely at beyond redshift of 6, generally shows too short lifetimes. For example, like 2 orders of magnitude lower than the standard picture predicted. And here we are trying to build a inference model for a method to measure the for the quasar lifetime, that is the transverse proximity effect. Imagine we receive the line of sight from the quasar and those background galaxies at the same time. These sight lines will also pass the quasar, the plane of the quasar at the same time. And for this sight line, before it passes this plane, it will also interact with the gas, like the blue distance divided by speed of light ago. And at this point, this gas is also like ionized by the light of the quasar, the blue distance divided by speed of light ago. So that is to say, this point in this space can probe the quasar activity like this total time ago. And if we fix the delta t, this time delay, this equation will give us a parabola in this space. That is to say, the points on this parabola in the space are probing the quasar activity at the same time ago. And now we know we can convert the line of sight co-moving distance to some redshift or wavelength if we look at a specific absorption, for example, the lambda alpha. And if we assume the quasar had a sudden switch on and set the delta t to the lifetime of the quasar, and this parabola, the resulted parabola will mark a transition from the background opaque gas to the foreground transmitted gas. And the lifetime of the quasar can be measured by, indicated by the size of the parabola. So the longer the lifetime is, the larger the parabola is. And at the same time, quasars are usually like obscured by a dust torus, so there can be an opening angle. So the lambda alpha transmission enhanced region is confined by both the parabola, which is not shown here, as well as the orange opening angle. As Christina has just talked about, the near spec data for a set of like background galaxies in the Eiger survey is coming soon, and with this about 24 galaxies, background galaxies, they will observe their lambda alpha transmission, lambda alpha forest, and we are trying to build an inference model using the transverse proximity effect to analyze this lambda alpha forest and to infer the quasars at least lifetime and opening angle. Oh, sorry. And okay, here we build we create a mock field of this field, and so the blue points are the sight lines, and we put this in the next simulation, and derived derived 1,000 samples for every sight line. So basically, the foreground is lambda alpha enhanced, transmission enhanced, and the background is opaque. And here are 2 examples of our sight lines, and we found that. Well, on the right is the correlation matrix, and we found like every sight line is correlated. So based on this, we built multivariate Gaussian model. So that is, we concatenate all the 24 skewers to form a big vector. Okay, so shall I continue?
Well, just summarize.
Okay. Okay, so. Okay, based on our 1,000 samples, we can form a big vector. We can compute the average of the big vector as well as the covariance, and we can also change the Quasar's model to change the lifetime and opening angle, and try to. And we also conducted a preliminary experiment. So that is to draw a random sample from the 1,000 skewers and 1,000 samples, and add noise to it, and conducted a preliminary inference on the Quasar's model. And we found, well, this can result in very accurate and strong constraints, even if we assume signal-to-noise ratio is 1. And thanks.
Thank you.